You might be familiar with this summation, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. This is just pi squared over 6. A very surprising result, and we can condense it into this summation. Have you ever considered, however, what is 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared, and so on infinitely? Now this over here, we're only taking the sum where the denominator is an odd number squared. So we're basically, from here, we're omitting all of the fractions with an even denominator squared, right? So how do we solve this? Well, I have a note to make before we get into it. If you're familiar with this summation, but you don't know how to prove it, or if you're just not familiar with this at all, then welcome to this video. When I evaluate this summation, it will give you a huge hint on how to evaluate this original summation. So stick around if you're not familiar with this. Okay, so we're going to start with trigonometry and calculus. Might seem a little bit strange, but it will work. So we're going to start with cosine of x. All right, cosine of x. Now, if you're familiar with the Taylor series of this function, it is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, and then so on and so forth. It's an alternating sum, and basically the exponent here is always even, and the factorials is always an even number factorial, right? And now we're going to examine when is cosine x 0? Well, we know that one value exists. There's pi over 2. Pi over 2. This is when cosine x is 0. We also have 3 pi over 2. 3 pi over 2 is another value. Are there any more? Yes, because cosine x is periodic with a period of 2 pi. Meaning if you add 2 pi on these sides, on both of these numbers, you will get another value for which this is 0. So if we add 2 pi to this, we get 5 pi over 2. And if we add 2 pi to this, we get 7 pi over 2. And basically, as you continue adding periods, you'll eventually realize that the values are basically just some odd number times pi and then divided by 2. Now, we can also go in the reverse direction. We also know that we can subtract this by 2 pi. If we subtract this by 2 pi, then it yields negative 3 pi over 2. And if we subtract this by 2 pi, it yields a negative pi over 2. And now we can just subtract in 2 pi in this direction, right? So subtract 2 pi, you'll eventually realize that you see another pattern. So it's basically the same thing, except it's a negative odd integer times pi and then divided by 2. This just goes on forever. So now that we have the zeros, or like the roots of cosine x, how do we use this at all? Well, notice that the Taylor series is basically just writing cosine x as like a polynomial, sort of. It's not a polynomial really, I should say, because it's infinite terms, more like a power series. However, notice that it doesn't really violate the conditions of a polynomial, right? Other than the fact that it has infinitely many terms, right? But other than that, it's just a polynomial because it's just the variable raised to a positive integer value. So, and this is the part where I'll be missing a few rigorous details, perhaps, because this is more like an intuitive claim than an actual proof. But it still works. Don't worry. So here we're going to make the claim that since this is like a polynomial, we can factor it as the product of linear factors, just as how you would with a normal polynomial, right? So for instance, you should know that if you have a polynomial with roots r1, r2, r3, and so on, right, maybe to rn, n roots, then you can factor this polynomial as x minus r1, x minus r2, and so on and so forth, right? And if there's a leading coefficient like a, then times a. But the point is that you can always factor it as a product of linear factors with the roots. So we're going to make the claim that we can factor this cosine x series as you would with the normal polynomial. Now it's a bit confusing on how to really do this, but there is a good way to factor it as we wish. So we're going to factor it like this. we're going to first deal with the positive roots. We'll first write one factor as 1 minus x divided by pi over 2. Might seem a bit strange, but here, notice if you plug in x for pi over 2, this is just 1, and 1 minus 1 is 0, right? And similarly for 3 pi over 2, we'll write it as 1 minus x over 3 pi over 2. Again, same reason. This would just be 1 when x is 3 pi over 2, and 1 minus 1 is 0. And we can basically continue this infinitely. So I claim that the polynomial shall be factored like this. And for the negative roots, it's the same story. It's just 1 plus x divided by pi over 2, right? And 1 plus x divided by 3 pi over 2. And 1 plus x divided by 5 pi over 2. So on and so forth. Okay, so now, as you can see, we have a difference of squares available to us. Notice that this is minus x over pi over 2. This is plus x over pi over 2. Minus plus minus plus. That yields a difference of squares, right? So we can combine them into a difference of squares like so. 1 minus x squared over pi squared divided by 4. And this here would be 1 minus x squared divided by 3 squared pi divided by 4, right? And here you would have 1 minus x squared over 5 squared pi divided by 4. Okay, good progress. I'm going to erase these roots now. All right, so notice that, well, first of all, let's simplify these things. We don't really like it when there's a fraction on the bottom, so I'm just going to write it as 1 minus, and this will be 4x squared over pi squared. And yeah, we're just going to do some quick rearranging because why not? But consider, after we've done that, what could we even do to proceed? Oh, sorry. Yeah, this is 3 squared, sorry. Okay, anyway, what could we do to proceed after doing this? Well, we can actually multiply all of these terms out, right? And the term that we're specifically interested in is the x squared term, right? Now, the reason that this works is because the constant term, as you'll realize, is 1. If you multiply all of this out, the 1 times 1 times 1 and so on will only be 1. And this matches with the constant term. So now all we got to do is match up the x squared coefficients with the x squared coefficients. How do we do that? Well, consider this. If you multiply this term over here by this 1 here, then you would get negative 4x squared over pi squared, right? We're collecting the x squared coefficients. And now, over here, if you were to multiply this one with this term over here, you would get negative 4x squared over 3 squared pi squared, right? And again, 1 squared times this term over here with an x squared again, this would be 4x squared over 5 squared pi squared. And you can continue this, basically, so it's just going to be 4x squared over 7 squared pi squared. And doing this infinitely, well, if we do this infinitely, we'll see that it's just the sum, or each term of the sum is 4x squared divided by odd squared times pi squared, right? Now, this, because it's an x squared term, this should be equal to this term, negative x squared over 2 factorial. Now, if we were to factor x squared out, so I'll erase everything up here. If we were to factor x squared out, rather, if we factor out, let's see, right, if we were to first factor x squared out and divide both sides by x squared, because we're just looking for the coefficients, we would find negative 4 over pi squared minus 4 over 3 squared, sorry, over 3 squared pi squared minus 4 over 5 squared pi squared, and so on. This over here is just equal to negative 1 over 2, right? So now, notice if we factor out negative 4 over pi squared, oh, let's try that again. Let me write that again. If we factor out negative 4 over pi squared, then inside we would just have 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared and so on infinitely. This is negative 1/2, right? This is the sum that we always wanted, right? This is the sum that we wanted to compute. If we just take the proper manipulations, multiply both sides by pi squared and then divide by 4, we would quickly see that 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared infinitely onwards. This would be pi squared divided by 8. And this is the sum of all of the reciprocals of odd squares, right? So this is our answer. Now, using a similar procedure, could you get the original sum? 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, so on infinitely. Could you prove that this is pi squared divided by 6? Shouldn't be that hard now, right? If you still need a hint, no problem. Just use the Taylor series of sine x. There you go. Try it for yourself. And by the way, since we know that the sum of the odd reciprocal squared is pi squared over 8, then all you need to do to find the sum of the even reciprocal squared is just take pi squared divided by 6 minus pi squared divided by 8, compute their sum, and then do a bit of simplification, and you have our answer. This is the sum of even reciprocal squared, and this over here is the sum of odd reciprocal squared. So what do you think? If you found this useful, helpful, interesting, please consider subscribing and dropping a like. Thank you.